students, welcome to 60 out of 60 in KCET Chemistry 2025 series in just 200 days. So yes, today we are going to start the last chapter of PU2 chemistry syllabus, that is Biomolecules, and in this video we are going to study about carbohydrates. And one more request, please join our WhatsApp channel. The link of the WhatsApp channel will be there in the description section of this video. If you join the channel, you can get easily access to the PDF of these notes, mock test and its solutions. Okay, so that will be beneficial. Please join the WhatsApp channel. Okay, and as I say you in my every class, please sit with a notebook and a pen and then watch this video so that you can make good study notes. You can note down what are the important topics. You can practice some questions with me. Okay, so yes, now without any further delay, let's get started to today's video. And please remember, this is the last chapter, so we should be full motivated that after this chapter the chemistry PU2 syllabus is done. Okay, so yes, now coming to the chapter division, as I discussed in my all chapters, part 1 will be part 2, part 3. So this chapter again will be covering in 3 parts. The first part will be carbohydrates, in the second part we will be doing proteins, and in the third part we will be doing enzymes, vitamins, nucleic acids and hormones. Okay, so today's video we are going to cover most important, most lengthy topic of this chapter, that is carbohydrates. Okay, now if you see weightage year wise, that you can see 2024 3 questions, 2023 4 questions. So easily I can say 2 to 4 questions you can expect from this chapter. Okay, and this is a completely theoretical chapter, very easy to score. So you can see 3 questions have been asked from the last 2017 to 2020. So yeah, must do topic. Okay, now coming to carbohydrates. So first of all, what are we going to study in carbohydrates? Its classification, monosaccharides, disaccharides and polysaccharides. Okay, then under monosaccharides again we are going to study about the classification of monosaccharides, preparation of glucose, structure of glucose, cyclic structure of glucose and structure of fructose. Okay, then under disaccharides we are going to study these 3 disaccharides, that is sucrose, maltose and lactose. And under polysaccharides we are going to study starch, cellulose and glycogen. Okay, so this will be the topics that we are going to cover in our today's class. Okay, so first let us go to classification of carbohydrates. So now if you see classification of carbohydrates, so carbohydrates are classified on the basis of 2 things. One is the products of hydrolysis. Now what is products of hydrolysis? When you break a carbohydrate, how many simpler compounds are formed? Okay, when you break a carbohydrate, how many simpler compounds are formed? Based on that there is some classification, and that basis is called as your products of hydrolysis. Now under products of hydrolysis we have 3 types of carbohydrates, that is monosaccharide, oligosaccharides and polysaccharides. Now what is monosaccharide? Monosaccharides are those carbohydrates which cannot be hydrolyzed further, which cannot be hydrolyzed, okay, which cannot be hydrolyzed further. Okay, means which cannot be hydrolyzed further means these carbohydrates are already in their simple form, it cannot be broken down further. Okay, now next category is oligosaccharides. Now what is oligosaccharides? Oligosaccharides means if you break this carbohydrate we will get 2 to 10 smaller units. Okay, 2 to 10. Now if you polysaccharides means if you greater than 10 smaller units, okay, then we call it polysaccharides. Clear? Now let us see one example from each category. Monosaccharides examples you can see like glucose and fructose. Okay, glucose, fructose means what? These carbohydrates you cannot break down them further. Okay, you cannot break down further them. These are the simple carbohydrates that is already present. Now oligosaccharides example is your sucrose. Okay, now if you break sucrose you can get 2 smaller units. Okay, if you break sucrose it will get converted to 2 monosaccharides. So that is why this is called as a disaccharide. We'll study about it in some time. Polysaccharides, you can have starch, you can have glycogen. Okay, so these are the polysaccharides. If you break them, we will get many number of small units or many number of monosaccharides. Okay, a lot of monosaccharides can be obtained, greater than the 10 obviously. Okay, so these type of compounds are called as your oligosaccharides. Okay, now talking about reducing nature. Now what is reducing nature? So reducing nature means those carbohydrates which reduces Tollens reagent. Okay, which reduces Tollens reagent. Those are called, those on the basis of that we have reducing nature. Now what are the categories here? Reducing sugars and non-reducing sugars. Reducing sugars means they reduce Tollens reagent, and non-reducing sugar means do not reduce Tollens reagent. Okay, now if you see example for this, reducing sugar example is your glucose and non-reducing sugar example is sucrose. Okay, so glucose can react with Tollens reagent, but sucrose will not react with Tollens reagent. So this is how carbohydrates can be classified on the basis of their reducing nature. Clear? Fine. So this is all about the classification of carbohydrates. Clear? Now we'll go to the second topic of today's lecture, that is monosaccharides. And in the monosaccharides, our first topic is classification again. But here we are talking about the classification of monosaccharides. The previous one was the classification of carbohydrates. Now in the carbohydrate, one section was monosaccharides. Now how further monosaccharides can be classified, that we will discuss. Okay, so monosaccharides can be classified on the basis of two categories. One is the number of carbon atoms, another is the functional group. Now what is the meaning of number of carbon atoms? Now see, monosaccharides can have 3 carbons, then it is called triose, 4 carbons tetrose, 5 carbons pentose, 6 carbons hexose and 7 carbon heptose. Okay, and on the basis of functional group, if the carbohydrates or if the monosaccharides have aldehyde functional group, okay, aldehyde functional group, then we call it aldose. If the monosaccharide have ketone functional group, okay, then we call it ketose. Clear? If the monosaccharide has aldehyde functional group, then we call it aldose. If the monosaccharide has ketone functional group, then we call it ketose. Now what is the example of aldose? Here the example is glucose, okay, and here the example is fructose. So fructose has ketone functional group and glucose has aldehyde functional group. We'll study about both of them in detail. Okay, fine. Next, coming to after studying about the classification, now we'll study about glucose, the structure of glucose. Okay, sorry, the preparation of glucose. So glucose can be, first one method is the preparation from sucrose. Okay, sucrose is what? Sucrose is a disaccharide. Okay, it comes under oligosaccharides. Means if you break sucrose, we'll get 2 monosaccharide units. So you can see this reaction. This one is sucrose, C12H22O11. If you do acid hydrolysis, means if you break this sucrose, you will get one glucose, okay, and another is fructose. Now you may see that both of them has same molecular formula, but you should remember and you must know now what is the difference between glucose and fructose. This is an aldose, this is a ketose, right? So these two you can say functional isomers. Okay, so now glucose can be prepared by breaking sucrose. Now similarly starch, if you have discussed just now, it is a polysaccharide, right? So now if you break starch, we will get many number of glucose molecules. So you can see this reaction here. So this is starch, the general formula of representing starch, that is C6H10O5N, and if you do acid hydrolysis, we will get NC6H12O6. Why this is written N? Because this N represents many. Okay, a lot of glucose molecules can be produced by the acid hydrolysis of starch or cellulose. Clear? That is the preparation method. First is from sucrose, another is from starch and cellulose. So that means that this starch or cellulose must be made up of glucose. Similarly, sucrose must be made up of glucose and fructose. We will study about these disaccharides and polysaccharides in detail in some time. Okay, clear up to this? So till now what we discussed? Classification of carbohydrates. Next we discuss, our next topic is monosaccharides. Under that first we discuss classification of monosaccharides. Next we discuss about the preparation of glucose. Now we will go to discuss about the structure of glucose. Okay. So here again very important, what is the molecular formula of glucose? So now what we are doing is, we are doing the deduction of glucose structure. Means we will be having some reactions, we have done some experiments, okay, and we have seen certain reactions. Based on these reactions we have got certain conclusions, and by observing these conclusions we have finally developed, or we have finally come up to the structure of glucose. Okay, so that we will be seeing now what are the different reactions, what are the conclusions, and what are the observations of these reactions, and based on that what is the structure of glucose predicted. Okay. So first is the molecular formula of glucose, so that is C6H12O6. Okay, so we know that in glucose there has to be 6 carbon, 12 hydrogen and 6 oxygen. Okay, that's the first thing we know. Now second, what we do now to understand how these 6 carbons are present, whether it is present in a circular ring or whether it is present in a linear chain or there is some branch chain, we do this reaction, that is reactions with HI. Now what happens here? If you react it, glucose we represent like this. Okay, this is the structure of glucose. Now if we react this with HI, okay, we get N-hexane. Okay, N-hexane, if you draw the structure, we have CH3, CH2, 4 and then CH3. Now from this what conclusion we get? Like what can you infer from this? Or I can say, what does this reaction tells us? What is the outcome of this reaction? This reaction tells that the 6 carbons of glucose, okay, 6 carbon in glucose, 6 carbons in glucose are in a straight chain, are in a linear chain. Right? That is the first thing we understand, that the 6 carbons of the glucose are not any branched way or not in any cyclic ring, rather they are present in a straight ring. Which reactions tells us that? This reaction tells us reaction with HI. Okay. Now coming to the third reaction, that is reaction with NH2OH or HCN. So now if we react them like this, I told you the structure of glucose, COH, you have CHOH whole 4 and then you have CH2OH. Now if you react it with NH2OH, okay, so here we will get a product like this, NOH, then we have CHOH whole 4 and then we have CH2OH. And then if you react it with HCN, okay, then we got COH, CN, then we have CHOH whole 4 and you have CH2OH. Right? Now these reactions might seem very similar to you or familiar to you, must have studied during the reactions of aldehydes and ketones. Right? So what does this reaction suggest? This reaction with NH2OH or HCN, what is the conclusion here? So I'll write here conclusion. See that these reactions are shown by what? Both aldehydes and ketones. So we can say that glucose has aldehyde or ketone group. right? That is the conclusion here. We don't know whether it is aldehyde or ketone. Now I am drawing this structure because now the structure has been already known, but before, when we do not know the structure, when we were not knowing the structure, at that time these reactions were done to deduce the structure of glucose. Okay, so second reaction was done, the reaction with bromine water. So what happened? So what is bromine water? Bromine water is a mild oxidizing agent. Okay, so now we know that mild oxidizing agent can convert CHO group to COOH group. So if there is an aldehyde group, in case we think that if it is an aldehyde group, then this reaction will convert that aldehyde group to ketone group, right? So what happened here? We took CHO, again CHOH whole 4 and CH2OH. Okay, now if you treat it with bromine water, okay, we found this product COOH, CHOH whole 4 and then CH2OH. Now this product is called as gluconic acid. Okay, this is called as gluconic acid. Now what conclusion does this reaction gives you? Conclusion, now it is clear whether it is an aldehyde group or ketone group. So the carbonyl group here, the carbonyl group in glucose, is nothing but a is a aldehyde group. Clear? So now we understood what all things. First we reacted with HI and we got that the 6 carbons are in one chain. Next we treated with HCN and NH2OH and these reactions are shown by aldehydes and ketones. So that gave us a conclusion that in a glucose molecule there has to be one carbonyl group. Now to confirm whether it is aldehyde or ketone, we reacted with bromine water and we confirmed this aldehyde got converted to acid, gluconic acid product was formed, and we confirmed that the carbonyl group which we suspected was present is present, and that is none other than the aldehyde group. Okay, till now we have done like 3 reactions. Next, coming to the reaction with CH3CO whole 2 CO. Now what happened if you react with this one, CHO, CHOH whole 4 and then CH2OH, and you react it with CH3CO whole 2O anhydride. So you know alcohols group react with anhydride groups to form esters. So what we will get? CHO, CHOCO, CH3. This is 4 times. Then we have CH2OCO, CH3. You can see here we have formed a pentaacetate. Okay, this is product is pentaacetate. Now what is the conclusion drawn from here? Conclusion. So if there is a formation of esters and there are 5 esters formed or 5 ester groups are present, the conclusion here tells that there are 5 OH groups present. Okay, 5 OH groups are present in this glucose molecule. Okay, next coming to reaction with HNO3. Now HNO3, if you know what is this is an oxidizing agent, right? So now here what happens if you treat this one, it is a strong oxidizing agent, right? So now if you see what we got, the product CHO, CHOH whole 4, CH2OH, and if you treat it with HNO3, concentrated nitric acid, we got COOH, CHOH whole 4 and COOH. Now this shows that, okay, we know that previously there is one aldehyde group, so we got one acid group which got oxidized, but another acid group is also formed here, and we know that primary alcohols can give you acids under strong oxidation condition. So what is the conclusion here? So the conclusion here that we got is there are 5 OH groups we have already got in the first graph. So out of this 5 OH group, 1 OH group is primary and 4 OH groups are secondary. These are the conclusions that we got from doing the different reactions of glucose. First one, reaction with HI, it tells that there are 6 carbons in one line. Second one, reaction with HCN or NaHSO3, that tells HCN or NH2OH, that tells that there is a presence of carbonyl group. Third reaction with bromine water confirms the presence of aldehyde group. Fourth one, reaction with anhydride confirms the presence of 5 OH group. Sixth one, reaction with nitric acid confirms the presence of 4 secondary OH group and 1 primary OH group. Okay. So now with these reactions we got the structure of glucose like this. Okay, this is the structure of glucose. Now what does this D represent? What does this plus represent? So plus represents here dextrorotatory. Means here if this compound is allowed if plain polarized light is passed through this compound, then it will rotate the polarized light, plain polarized light clockwise. Okay, that is why this plus is there. Now what does this capital D represent? So capital D doesn't stands for dextrorotatory. Okay, that is a different thing. So here what happens, we have a something compound like this, CH2OH, CHO, OH and H. This is important compound, that is your glyceraldehyde. Okay, now with reference to this one, if this OH is on the right hand side we call it D. If the OH is on the left hand side we call it L. Which carbon? The last asymmetric carbon. Okay, so if you see, this is the last asymmetric carbon, right? And here this OH is present on the right side, and due to this OH present on the right hand side we call it D plus glucose. Okay, so this capital D represents the configuration of the last asymmetric carbon. Clear? So that is how is the structure of the glucose we finally deduce. Okay, next we have some limitations with this linear, or you can say open chain structure of glucose. This is called as open chain structure of glucose. Open chain structure of glucose. Okay, this is the open chain structure of glucose. Now but we found that there are some reactions which this open chain structure should show, but it doesn't show those reactions. Okay, so here comes the limitations of open chain structure. The first limitation is it does not react with Skiff reagent and NaHSO3. If it has an aldehyde group, then it should react with Skiff's reagent and NaHSO3, but we find that there is no reaction with these two groups. Okay, next, pentaacetate does not react with NH2OH, indicates the absence of free CHO group. Okay, so there is no CHO group. Then we found that the glucose can exist in two different forms, that is alpha and beta. Okay, so these three limitations could not be explained by the open chain structure of the glucose. Okay, so that is why it was proposed that one of the OH group may add to the CHO group and form a cyclic hemiacetal structure. Okay, so to explain these observations, what the scientists thought that one of the OH group might react with the CHO group, means this one of the OH group might react with the CHO group to form what? To form a hemiacetal ring, to form a hemiacetal structure. This explains the absence of CHO group and also the existence of glucose in two forms as shown below. So now you can see here what they are saying. To explain these limitations, we said that glucose can have another structure also. So here this OH forms a bond with this carbonyl C. Okay, and then if this is forming here, we'll get OH and H on this carbon, that is OH and H on this carbon, OH and H on this carbon. So now this carbon has become also asymmetric or chiral, so OH can be present either this side or this side. So one form is called as alpha, other form is called as beta. Now this is a ring structure. Okay, this is a ring structure. Okay. So now this structure explains these limitations. Now because there is, if this one is formed, there is no more aldehyde group. If there is no more aldehyde group, it will not react with Skiff's reagent or NHSO3. It will not react with NH2OH, right? And we can also explain the existence of alpha and beta form. Now if you see, this doesn't look like a ring structure, right? It is a straight chain. So there we can represent it as a ring structure, and this form of projecting the ring structure is called as Haworth projection, okay, given by the scientist name Haworth projection. Okay, now how to remember, how to draw this one? So if you remember here, this is your alpha form, this is your alpha form, right? So whichever is on the right hand side, okay, right hand side will be at the down and the left hand side will be at the top. So just a trick here, okay. So now you see, this is C1, this is C1. OH is present on the right hand side, OH is down, H is up. Next one, again OH is present on the right hand side, so down, up. Next you see H is present on the right hand side, so H is down. Fourth one, if you see, OH is on the right hand side, so OH is at down. Like this you can draw the structure of alpha D glucose. Now similarly, everything else is correct, everything else is same, only this carbon configuration changes. Okay, what happens? This changes, OH goes up and H comes down, and this particular conformation is called as beta D glucose. Okay, now here you can see a name pyranose is there, glucopyranose and alpha pyranose. What is this pyranose? Why this name is used? So that is because of its similarity with a structure called as pyranose. Okay, we'll see that. Now see, one more important definition is anomers. So what I can say, if the configuration, okay, if the configuration of two structures differ only at the carbon number 1, here you see all other configurations are same, right? Only at carbon number 1 it is different. So such type of isomers where the complete structure is same but only at first carbon the structure or the conformation is different, those type of compounds are called as anomers. Clear? So what is alpha D and beta D glucose? These are anomers. Now I was telling you why they are called as pyranose, because their structure is somewhat similar to a compound called as pyran. Okay, so you can see this is the structure of pyran. Its structure somewhat resembles towards this pyran, that is why it is called as glucopyranose and alpha D glucopyranose, beta D glucopyranose. Okay, so alpha you should remember OH should be at down. Okay, for alpha OH is down and for beta OH is up. Okay, alpha OH down, beta OH up. Okay, so and if the conformers are different at one single carbon, that is called as anomers. Clear? Okay. Now we will go to the next topic, that is structure of fructose. So glucose we had done, we saw its preparation. We saw 6 reactions which define the structure of glucose, open chain structure. Then we saw the limitations, and after that we saw the cyclic structure of glucose. Now coming to structure of fructose. So this is a structure of fructose, and I told you this is a ketone group. Okay, and this has also 6 carbon, so this is also hexose group. Okay, now like we have cyclic structure for glucose, same way we have cyclic structure for fructose. So what happens, this carbon OH group, okay, it combines with this one and this bond shifts here, so we get a structure like this. Okay, now as we have alpha and beta in case of glucose, similarly we have alpha D fructofuranose and beta D fructofuranose. Now if you see fructose, we have negative, right? So this is what fructose is, levorotatory. So remember, glucose was dextrorotatory, fructose is levorotatory. Okay, now D stands for this OH group, right? This is on the right, this is also on the right, so that is why it is capital D represents the configuration of the last asymmetric carbon. Now here alpha means what? OH should be down, beta OH should be up. Now how we have Haworth structure for glucose? Same way we have Haworth structure for fructose also. You can see here alpha OH is down, and here you can see beta OH is up, and all other configurations are same. So these two are also your anomers. Clear? Okay, now coming to why they are called furanose, because their structure is somewhat similar to furan. Okay, one compound. So this is a 5-membered ring, right? 1, 2, 3, 4, 5, and glucose was 6-membered ring, but there are 6 carbon, right? So now see, this is a 5-membered ring. Okay, although there are 6 carbon, but the ring is made up of 4 carbons and it is a 5-membered ring. Okay, so that is why this is called it is similar to furan and we call it furanose. Okay, but again this, because it has in total there are 6 carbons, it is also a part of hexose. Okay, fine. Next, coming to the third topic. So first we discuss about the classification of carbohydrates, then we completed monosaccharides, and now we are going to discuss about disaccharides. So we'll be studying 3 important disaccharides, that is your sucrose, maltose and lactose. Okay, so what you need to remember, see this is one monosaccharide, okay, and this is another monosaccharide. Now these two monosaccharides are connected, okay, connected by a bond. What is the name of this bond? This bond is called as glycosidic bond. Glycosidic linkage. Okay, so let me write it clearly. So this bond is called as glycosidic bond. Clear? This bond is called as glycosidic linkage, which connects two monosaccharides. Okay, so for every disaccharide you need to remember 3 important things. First, okay, so first you need to remember about what are the monosaccharide units. Like this disaccharides is made up of what monosaccharides. Next, the linkage. Okay, which carbon of one monosaccharide is connected to which carbon of another monosaccharide. And the third one you need to remember is examples. Okay, now third one you need to remember is reducing or non-reducing. Reducing or non-reducing. Okay, so now coming to the first one is sucrose. Now sucrose is made up of D-glucose and D-fructose. Okay, sucrose is made up of D-glucose and D-fructose. So first thing done, what are the monosaccharides present in the sucrose? D-glucose, or you can say D-glucose and D-fructose. Now coming to linkage. So the linkage is between, you can see, C1 of alpha D-glucose, okay, and C2 of beta D-fructose. So C1 of alpha D-glucose and C2 of beta D-fructose. Now let us see that structure here. You can see this is glucose, right? Alpha D-glucose. Alpha means OHs should be present at the down, okay? And this is your beta D-fructose. C1 of this one, and this is carbon number 1 and this is carbon number 2. So C2 of beta D-fructose. These two structures form the glycosidic bond. Okay, these two carbons are involved in glycosidic bond. So what is there in linkage? C1 of alpha D glucose and C2 of beta D fructose. Clear? Next, coming to reducing and non-reducing. This is a non-reducing sugar. Clear? So these 3 points you need to remember about sucrose. Now we'll go to the next disaccharide. Okay, next, okay, one more thing here, important point about inversion we need to study. See, if you see sucrose is dextrorotatory, okay. If you just take a sucrose solution, okay, and then you pass plain polarized light through it, it will rotate in a clockwise direction, okay, and we call it dextrorotatory. But when it undergoes hydrolysis, okay, if sucrose undergoes hydrolysis, if in the same solution you add some acidified water and the sucrose solution starts giving you glucose and fructose, right? So slowly you will see after some time the plain polarized light will become levorotatory, means it will be rotated in the anti-clockwise direction. The solution will become levorotatory. Now what is the reason for that? So if you see sucrose, okay, is dextrorotatory. Now when it breaks, when it undergoes hydrolysis, we get fructose, okay, and glucose, okay. So glucose is dextrorotatory and fructose is levorotatory. Now the levorotatory of fructose is minus 92.4. Okay, so it is the levorotatory of fructose is more than the dextrorotatory of glucose. So which is more dominant here then? Levorotatory fructose, right? Because it is having more degree of rotation. So that is why overall the solution now becomes levorotatory, and this phenomenon is called as inversion of sugar. Okay. Earlier it was dextrorotatory. Once it undergo hydrolysis, fructose is formed, glucose is formed. Fructose levorrotation is more than glucose dextrorotation. So fructose dominates the solution and it rotates the plane polarized light in anti-clockwise direction, and we call it, the solution becomes now levorotatory. Clear? Okay. Now coming to the second disaccharide, that is your maltose. Again we need to study in 3 points. What is our first? We will study about monosaccharides. Second we will be studying about the linkage, right? And third one we will be studying about whether it is reducing or non-reducing. Okay. So what are the monosaccharides in maltose? So monosaccharides in maltose, so you can see maltose is composed of 2 alpha D glucose units. Means the monosaccharides here are nothing but alpha D glucose units. Now what is the linkage here? Here the linkage is between C4 and C1, right? C1 of one glucose is connected to C4 of another glucose. Now it is a reducing sugar. Now how to tell whether it is a reducing sugar or not? So there is a trick for that. You need to find hemiacetal form. See, if the disaccharide has hemiacetal, then it will be reducing. If there is no hemiacetal form, then it will be non-reducing. Now what is hemiacetal form? If you remember hemiacetal, we have studied hemiacetal is COHOR. If you can find any group like this, COHOR, then it will be reducing in nature. Now let us see this one. So if you see maltose, this is alpha D glucose, this is also alpha D glucose, right? This is C1 and this is C4, right? Now here there is a glycosidic linkage. Okay. Now you see this carbon. This side it is OR. I can say this is OR, this is also OR. So there is two sides OR for this carbon. So this is a hemiacetal, this is a acetal, not a hemiacetal. But if you see this carbon, here you see this side it is OH and this side it is OR. So this carbon has hemiacetal form. So that is why this whole sugar behaves as a reducing sugar. Okay. Now if you compare it with sucrose structure, you see this carbon OR, here OR, here again, here there is no OH, right? And here also if you see there is no OH, here also OR, there is no OH and OR attached to the same carbon. That is why it is non-reducing sugar. Okay. Next, coming to your third disaccharide, that is lactose. Again we will be talking in the same way. What are the monosaccharide units, what is the linkage, and what is whether it is reducing or non-reducing. So first of all, if you see, it is composed of beta D galactose and alpha D glucose. Okay. So we have beta D galactose and alpha D glucose, the monosaccharide units, and the linkage is between C1 of galactose and C4 of glucose. Okay. So if you remember here, C1 of galactose and C4 of glucose. So we can see here, this is galactose. Okay. So if you see what is the difference between galactose structure, at C4 position these two are different. Okay. At C4 position, for galactose OH is present in the above, OH is present at the top, and for glucose the OH is present at the bottom. Okay. And all other configurations are same. Now here this is C1 of galactose and C4 of glucose, right? So that is the linkage form, and this bond is nothing but your again glycosidic linkage. Okay. Now coming to whether it is reducing or non-reducing. For reducing, what we need? We need hemiacetal group. We need to search for a hemiacetal group where it should have COH and COR group. So if you see here, there is no OH, so we can remove this one. And if you see here, see you see OH is there and COR is there. So definitely this is a hemiacetal group. So this sugar is a reducing sugar. Okay. So what you have to do, how you need to remember, how you need to prepare short notes for this one. See, I'll tell you. You prepare like this. Make a table Okay, you need to make a table. Okay, first column, name of the disaccharide. Second column, write down the monosaccharides name. Third column, write down the linkage. Fourth column, write down reducing or non-reducing. 1, 2, 3. So your homework is, after studying this one, all of you need to make this table and keep it in your short notes. Okay, I hope after doing the homework, if you have written this, please put down in the comment section that you have made this table. Okay, fine. Now let us go to the last topic, that is your polysaccharides. Polysaccharides, as I told you, when you break these saccharides, we get many number of monosaccharide units. So our first polysaccharide is starch. Okay, we are going to study first one, starch. Now if you see starch here, what is the, again it's the same thing, it should be made up of some monosaccharides. So it is a polymer of alpha glucose and consists of two components. So starch has, like the monosaccharide is alpha D glucose, okay, but it has two components, one is amylose and another is amylopectin. What is the difference between these two? See, amylose is water soluble, amylopectin is water insoluble. Majority of the starch is amylopectin, 80 to 85%. And amylose is only 15 to 20%. Now unbranched chain. So in amylose what happens? There is no branching, it is a linear chain, and here you can find some branch chain. Now what is the linkage? Alpha D glucose C1 to C4 linkage is there. Okay, so and polymer of alpha D glucose units in which the chain is formed by C1 C4 glycosidic linkage, whereas the branching occurs at C1 C6 glycosidic linkage. Okay, so for the linear chain it is C1 to C4, and for the branching it occurs at C1 to C6. We'll see the structure now. This is amylose, a straight chain of alpha D glucose is there, right? How can I say these are alpha D glucose? Now you see, at alpha means OH will be at the bottom, right? Here OH is present, here OH is present, here OH is present. This is C1, this is C4, this is C1, this is C4. So there is C1 C4 linkage, and this forms a straight chain. Okay, and this is your amylose. Now if you talk about amylopectin, so this is a chain connecting and this is a chain connecting. This amylose ring is going on, amylose ring is going on, but there is a linkage between C1 and C6. Okay, so if you see, this is C6, this OH is there, right? So this OH forms bond with the C1 of the upper layer. So that is how we get a branch chain. Okay, so you have to remember, in amylose it is a straight chain of C1 C4 linkage, but in amylopectin it is a straight, it's a branch chain where there is a C1 C4 linkage and the branching occurs at C1 C6 linkage. Okay, fine. Now coming to the next polysaccharide, that is cellulose. So cellulose also contains your, okay, here cellulose is made up of beta D glucose units. Okay, there are many number of beta D glucose units which have combined to give you cellulose. Okay, remember, starch alpha D glucose, cellulose beta D glucose. Okay, now the cellulose, what is the use? It is a main component of cell wall in plants, right? Now if you see the structure here, this is one glucose unit, right? So this is your beta carbon, you can see OH is present at the top, and the linkage is between C1 to C4, again C4, and this is C1. Here it is C4, it is C1, right? So what I can say, the linkage, about the linkage, C1 to C4 beta linkage, right? Clear? Okay. C1 to C4 linkage is there. Monosaccharide units are your beta D sucrose units. Okay, beta D glucose units. Okay. Next, coming to polysaccharide, next one, that is your glycogen. Okay, so glycogen, if you see, the what is the use? The animal fats or the animal energy is stored in the form of glycogen. It is also known as animal starch. Okay, and the structure is similar to amylopectin, but it is more highly branched. So that means, if you remember, the structure, if similar to amylopectin, means it one has C1 C4 linkage and the branching occurs at C1 C6. Okay, but this branching is more frequent or more intense in case of glycogen as compared to amylopectin. Okay, next, what other uses are there or where it is found? It is found in liver, muscles and brain. Okay, so whenever our body needs glucose, enzymes break down the glycogen to glucose. Okay, so because glycogen are made up of your glucose units, and which glucose units? These are your alpha D glucose units, right? So whenever your body needs energy, the glycogen present in the animals are converted to glucose by enzymes. Okay, so these are also found in yeast and fungi. Clear? Okay, so that's all about the carbohydrates. We have discussed everything about carbohydrates. Now it's time to solve some questions. Okay, fine. The first question, sucrose is not a reducing sugar, because if you have seen, there is no OHOR group, so it is chemically stable. It contains no free aldehyde group or keto group adjacent to the CHOH group. Okay, so whenever there is a free aldehyde group, that type of sugars are having your what we reduce means reducing means what? It should react with tolerance reagent, right? So it should have a free aldehyde group, but sugar sucrose does not have a free CHO group. That is why it is a non-reducing sugar. Okay, next one, how many monosaccharides are obtained by hydrolysis of sucrose? So we get two, one is glucose, another is fructose. That's why it's a disaccharide. So correct answer is option number B. Okay, next, which of the following does not reduce Benedict solution? So Benedict solutions are reduced by aldehydes or ketone groups. Okay, so sucrose does not have free aldehyde or ketone group, so answer is option number B. Next, the pair of compounds showing positive tolerance test means they are reducing sugars. So glucose and fructose are reducing sugar, so they will show reaction with tolerance test. So correct answer is option number C. Next, which of the following statement is correct? Okay, a polymer of alpha glucose is readily digested by human beings but not that of beta glucose. Yes, that is correct. Alpha glucose polymers can be digested, but we cannot digest cellulose, right? So cellulose are made up of beta glucose, so that is why the correct answer is option number A here. Next, which of the following is a linear polymer? So linear polymer, we have just discussed amylose is a linear polymer, like amylopectin is a branched polymer. Glycogen structure is also similar to amylopectin, so that is also branched. Next, galactose is a monosaccharide, right? It was found under what? Lactose. It is a component of, or you can say a component of lactose. Okay. Next, glucose gives silver mirror with ammonical silver nitrate because it has a free aldehyde group. Okay, correct answer is option number A. Next, sucrose is dextrorotatory, but after hydrolysis the mixture shows levo-rotation. This is because levo-rotation of glucose is more than dextrorotation of fructose. No, I told you glucose is dextrorotatory and fructose is levo-rotatory, right? Sucrose is a non-reducing sugar, it has no relation. Racemic mixture, no. Levo-rotation of fructose is more than the dextrorotation of glucose. That is option number D. Okay, how much more it is? It is more by minus 92.4 degree. Okay, next, the two forms of D-glucopyranose are, means what is the relation between alpha and beta? Just we discussed, the configuration is different at only C1 position, so that is called as your anomers. Okay, so yes, now a homework question, the glycosidic linkage involved in the units of amylose part of the starch. Okay, so that you have to find out. Okay, find comment this answer in the comment section. Okay, so students, that's all for the carbohydrates. You can practice more questions, and if you have liked this session, please do not forget to subscribe the channel, join the WhatsApp channel, and do not forget your target, that is 60 out of 60 in KCET Chemistry. See you soon in the next class where we are going to start proteins. Okay, thank you and take care.